Let's get started. We've now entered a whole new phase of the course, and for, maybe 4 weeks or so, what we're going to talk about are different kinds of chromatography. And we're going to start, as I said the other day, with gas chromatography. And then we're going to move into various kinds of liquid chromatography, and then eventually we'll get to capillary electrophoresis, which is not chromatography, but is very closely related. And then at the end of the semester, we'll talk about detection and quantitation, which is sort of an added-on subject to separations, but analytical chemists need to know about detection and quantitation pretty well. So, and it's different in chromatography in a number of ways from ordinary quantitation. And of course, the detectors we use in chromatography are not necessarily the same as the detectors we use in other fields of analytical chemistry. So that's the way things are going to go. So we're going to be talking about different kinds of chromatography for the next several weeks. This is the first gas chromatogram ever obtained. It came out of a paper by Singh and Martin. I think this paper was 1952. This big curve down here, let me get my pen activated. This curve down here looks like a chromatogram. And it is a chromatogram. But that's not what they did. They didn't have detectors that were worth anything at the beginning. The separation that they were doing here was a separation of the lower carboxylic acid. So it's acetic acid, propionic acid, So the stuff that's coming out the end of the column in the gas phase are acids. So what they did is they bubbled the acids through water and they titrated. And this is the titration curve. And so this first one is acetic acid. I think this is the acetic acid. And then propionic acid, and then butyric acid, and so on. You can't see the data points because it's not well enough, but the endpoints volumes are plotted here. So these various points are a measure of how much acid has come out. And so they take the first derivative of this, and that's what they plot here. So this is the derivative of all of the titration curves. And you can see that it worked. There's a beautiful separation of a bunch of carboxylic acids. I dare say it's the best separation of carboxylic acids that anybody had ever seen up until this time. That was about 1952. This is about 1955. Raymond Desti at I think it was the Dutch oil company, Royal Dutch Shell in Britain laboratory. He set up one of the very first capillary GC columns, and in 3 hours and 27 minutes. He generated 1 million effective plates. Now remember, effective plates is smaller than plates because of the K-prime factor. This was, mind-boggling separation. He had to make his own column because there was no commercial supplier. He had to make his own detector. I think it was a flame ionization detector, which had recently been developed. And, you know, this is another mind-bogglingly good separation. And GC was on its way. GC, by the way, is still, in terms of dollars of instrumentation, about equal to liquid chromatography. And forget about the detector and just the instrumentation and the columns. And it's considered a mature discipline, a mature subject matter. Most instrument companies that make them consider it a cash cow, because there's not a whole lot of new stuff going on in the GC world. So they're not putting a lot into research on it. Here's, I think, a very interesting chromatogram. The sample is the same in both of these. This is a packed bed chromatogram, and this is a capillary GC chromatogram. The sample is something called calmus oil. I imagine it's extracted out of some plant. The interesting thing here is the stationary phase is exactly the same. Both of these are OV1. When you read the GC literature, you're going to see all kinds of things like OV1, OV3, OV10. The OV is really complicated. It means the Ohio Valley Chemical Company, OV. It has no chemical significance other than that. So don't let it boggle your mind too much. But even though the stationary phase is the same, the sample is the same, you can see way, way, way more peaks up here than you can see here. I mean, this thing here is probably a collection of maybe 10 or 15 peaks. So it's not 2 peaks, it's a whole bunch of compounds that happen to just not separate well enough, peaks narrow enough so that you can actually see the spikes. Again, a clear demonstration of the vastly improved resolution available in a capillary system versus a packed bed. So, you've got to put this column in an instrument to make it work. And GCs are basically pretty simple. Of course, the heart of the thing is a column. Showing here a dual column system with dual detectors. The columns in GC are invariably placed in an oven because you've got to be able to adjust the temperature, and you've got to be able to hold the temperature pretty constant. You don't want the temperature wandering around by more than perhaps 0.2 degrees centigrade, something like that. If it's worse than that, you're going to see the peaks moving. The oven these days always comes with a temperature programmer, usually some kind of computer controller, so that you could do a very fancy program, not just one ramp, but a series of ramps and steps and holes and ramps at different rates. You've got to get your sample into the chromatograph, into the column, and that requires an injector. The injector is really, absolutely one of the most difficult parts of a gas chromatograph to deal with. It's one of the most complex parts of the system. If you screw up the injection, you're done. You're cooked. It's not going to work. I'm going to talk about packed bed injector. Injectors for capillary systems are much more sophisticated than injectors for packed bed systems. There are books just on injectors for gas chromatography, and there really need to be, because it's a very subtle, complicated process. Sample through the system, through the injector, over to the oven, over to the columns, and out to the detector is carrier gas. And that is very simply supplied by a tank, pressurized tank of that gas. The most common gases are helium and nitrogen. And until 5 years ago, that would have been absolutely unequivocal. But the price of helium in the world has gone up tremendously, and so there's really a major switch now to using hydrogen, especially in capillary columns. The flow of hydrogen may be a little bit too high in packed beds. The flow in capillaries is a lot lower. The kinds of regulators, pressure regulators that exist right on top of the tank are just not adequate to maintain the pressure properly. So there's always, between the tank and the rest of the chromatograph, a system of delicate pressure regulators that can really hold it quite constant, and also flow controllers. But basically, in most gas chromatography, the flow rate is set essentially by the flow restriction offered by the column to the pressure set on the regulator. So if you change the column, or the column diameter for some reason changes, or you chop off a couple of centimeters of the capillary and you change its flow resistance, your flow rate's going to change. If you change the temperature of the column, the flow rate's going to change. Now, in the past, I would say roughly 10 years, a lot of companies have started offering electronic pressure regulation, which means it's a computer-controlled pressure regulator. It also has flow regulation. That's a new thing. It is a very useful feature to have. Some gas chromatographs, especially those that are being used for measuring what we call permanent gases, methane, carbon monoxide. You can analyze oxygen, nitrogen, and so on, but you have to go to low temperatures. That requires accessories to get to lower temperatures. One of the slowest parts of doing gas chromatography when you're doing temperature programmed gas chromatography is when you want to do the next run, you have to cool the thing back down. And that is often slower than heating it up. And sometimes you will have a subambient accessory just to speed up the cool down process. And then the sample gets pushed out of the column by the flow of the carrier gas, and then over to a detector. And we won't talk about detectors until the very end of the semester. Gas chromatography, there must be easily 20 different kinds of detectors that are used. By far the two most common are the so-called flame ionization detector, which can measure virtually anything that burns. So anything that has carbon and hydrogen, CH bonds in it, you can measure with a flame ionization detector. Something like carbon tetrachloride, no. Perfluorocarbons, no. But almost anything else will give you a decent signal on a flame ionization detector. And then, of course, that feeds a data system to help you analyze the data. If you're doing preparative scale gas chromatography, you need a bigger instrument, bigger columns. Prep scale GCs I've seen as big as the height of this room, would take up a significant fraction of them. They're expensive. Okay, so I'm going to start off by talking about a bunch of practical issues in gas chromatography. One of them is what is the effect of carrier gas. And here they're showing the influence of three carrier gases, nitrogen and argon down here, and hydrogen here, and helium would be in between, but closer to the hydrogen. There's virtually no effect of the carrier gas on retention times, but there is this very big effect of carrier gas on your HETP. And the reason for that is that the diffusion coefficient of your analyte, the stuff you're measuring, the stuff that's giving a peak, depends upon what the carrier gas is. And the heavier the carrier gas is, the nitrogen, the argon, the slower is the diffusion coefficient of the analyte. So over here, where the B term of the Van Deemter is dominant, if you lower the diffusion coefficient of the analyte, the peak gets narrower. But if we went out to a high enough velocity, this curve would cross over that curve. And this is where the C term of the Van Deemter equation begins to dominate, and in particular, the C term corresponding to external mass transfer dominates. And as you decrease diffusion coefficient, that transport from the mobile phase to the particle gets slower and slower. So if you use a heavier carrier gas and you lower the diffusion coefficient of the analyte, you're going to screw up the C term, you're going to make it bigger, and the HETP is going to be bigger. So since most of the time we work above the minimum in the Van Deemter curve, because we want to do the chromatography fast, it is beneficial to use a light carrier gas, like hydrogen or helium. Okay, this is a GC injector for a packed bed. It is a little bit complicated, a little bit. Here's where you actually inject your sample, and right here there's a rubberized septum, and a syringe, either held by yourself or by an automated injector, goes through that rubber septum, and a syringe needle comes into here. And this is what we call the injection liner. It's usually made out of glass or quartz, and you squirt the sample in as a liquid. It hits the injection liner. The injection liner is heated because it's in a heating block. Here's the heating cartridge. This is all metal. The glass liner is in contact with a hot metal surface, so the glass liner itself is hot. So you inject your sample in a solvent onto the liner, and the idea is to vaporize it instantaneously. Now, the only way you can vaporize it instantaneously is you gotta have the liner above the boiling point of the sample. If it's below the boiling point of the sample, you just blew it. The recipe's gonna look like garbage. Now, the carrier gas comes in over here, comes up around the outside of the liner, and then passes down into the liner, and it's the flow of the carrier gas that sweeps the vaporized gaseous sample down, out, and over to your column. Glass is not nearly as good a thermal conductor as metal. Quartz is not as good a thermal conductor as metal. The question arises, why don't I make my injection liner out of stainless steel or something like that? That would be a good thing to do if you wanted to cook your sample and destroy it. We can't use metal. In fact, there's significant decomposition of many very fragile organics in the injection liner. Injection liners are normally chemically deactivated by washing them extensively with acid to get any metals that happen to be in the glass out of the glass. They have to be very, very, very pure. After washing them with acid, they are subjected to a process called silanization. And this chemically changes the surface of the liner to make it even less chemically active. And I'll tell you about the chemistry of this in a little bit. So that's the basic GC injector for a packed bed. This shows you the effect of two things, well, three things. What the nature of the sample solvent is, I forget what the solute is in this case, but they made the solute up in acetone and they made it up in dichloromethane. Both of these are pretty low boiling organic solvents. And then they injected 2 microliters or 3 microliters of sample in each of those solvents. And they did this as a function of the temperature of the injector. And this is the number of theoretical plates that the injector was essentially delivering. So the higher the number of theoretical plates, the narrower the peak is that comes out of the injector before it gets into the column. So we want as big a number as possible. There's a lot of data here, and I know it's hard to read, but there's several things that are very clear. Number one, the temperature of the injector is absolutely critical, and if you're at excessively low temperature, your peaks are going to be very broad. You're not going to instantaneously vaporize the sample. As you increase the temperature, it goes up and up and up. You see, even here, you gain a little bit by even going to higher temperature. And if your samples were able to handle a higher temperature, you should raise the temperature further. In fact, the temperature really has to be not just above the boiling point of the injection solvent, it has to be above the boiling point of the sample that you're interested in. If it's not, the solvent just goes out and you leave your sample in the injector. That's a disaster. So generally speaking, your injector is at the highest temperature of any part of your chromatographic system. And it's not uncommon to have the injector at 200, 250, even 300 degrees, if your analyte can handle those high temperatures. And this is probably the biggest limitation of gas chromatography. It really is only good for analyzing compounds that are thermally really, really stable, or compounds that can be chemically derivatized and made sufficiently volatile that you can chromatograph them without nuking them. So the temperature is a big deal. The acetone is a little more volatile than the dichloromethane, so it's giving somewhat higher plate numbers than the dichloromethane. And the third thing that's in here, but it's kind of buried in the details, is the larger the volume you inject, the worse the peak. But that should not be a surprise. However, let me point out that when you take a liquid and vaporize it, even at room temperature, its volume increases by roughly a factor of 1,000. 1 mole of ideal gas occupies 22.4 liters, right? 1 mole of methanol is about 100 mLs. So that's a factor of over 220. So this microliter, or 2 microliters of solvent goes like that. You want it to be fully contained in the liner so that it can enter the column as a plug and not as a big explosive mess. We've talked a good bit about temperature programming in GC way back when. This perhaps is a little better picture of why you want to do temperature programming. All the samples here are the same in all cases. This is the temperature program run at roughly the right temperature program. And you can see some 21 peaks that are all pretty good peaks. If we start over here at 75 degrees, in 24 minutes, the best we do is see 12 compounds. We see the normal isothermal progression, same amount of sample in each peak. The peak height comes down, peak gets wider. If we were to wait for compound 21 to come out sometime next week, you wouldn't see it because it would be so wide and so hot, just tiny blip. You wouldn't see it above the baseline wandering around. So that's why we do temperature programming in GC. Some GCs allow you to do flow programming where they deliberately raise the pressure at the inlet and speed it up. There are some slight advantages to that, but they don't really offer you nearly the flexibility that you can gain by changing the temperature. This goes back to the packed bed column, not a capillary column. Let me see if I have a picture there. This is a picture of the stuff that we put in packed beds. This is diatomaceous earth. This is I think a 5-micron marker. It's highly porous material. You can load it with a lot of polymer to function as the stationary phase. So what they're doing here is they've got some of that diatomaceous earth and they're loading it with different percent by weights of organic solvent. And this is 2% by weight organic solvent. And knowing the surface area of that diatomaceous earth, they're calculating that if the surface were uniformly covered, and that's a big assumption, that it's uniformly covered with the stationary phase, the average thickness of the stationary phase would be 3 angstroms. No, that's not much. That's extremely thin. And then they go and do a chromatogram, and I don't know what the mixture is here, but these are your chromatographic peaks. And they look pretty terrible. The surface is not uniformly coated. There are bare spots on the surface with no coating. And the sample is interacting with those bare spots and is desorbing from them slowly. And the more retained the solute is, and retention time is increasing in that direction, the more retained it is, the slower the desorption rate is, and you get some really horrid looking peaks. Now, as you load on more stationary phase, you do a better and better and better job of coating. This is now an 8 angstrom And you see a huge improvement by going from 2 angstroms, or from 3 angstroms to 8 angstroms. And it gets better, and it gets better. And this is 20% by weight stationary phase on top of the inert, so-called inert carrier. And then, when you get up to 30% by weight stationary phase, the peaks start to get wider again. So you can't put on as much stationary phase as you want, because ultimately the film gets so thick that diffusion in the stationary film now becomes a limiting factor in terms of mass transfer into and out of the film, and the peaks get wider. Well, there's the diatomaceous earth again. Okay, now, the stationary phase in the packed bed world and the capillary tubing in the open tubular world are never used out of the box, so to speak. They're chemically modified surfaces. You cannot deal with the surface of silica or diatomaceous earth or almost any inorganic solid, because it's chemically too active in terms of causing catalytic breakdowns of organic compounds. So invariably, the surface is chemically modified. In this case, I'm using a compound called hexamethyl disilazane, HMDS for short. Hexamethyl, 1, 2, 3, 4, 5, 6, disilazane, and that tells me that that's an amino group in between the two silane functional groups. This is extremely reactive stuff, and it goes after SiOH groups. In fact, it goes after alcohols, it goes after carboxylic acid, it goes after anything that has an OH group. And it reacts with it, and this half of the molecule gets attached. So this is like that. This is what I'm drawing. Now you've turned a surface which is polar, an SiOH group is a rather polar surface, into something that looks more or less like a hydrocarbon. It's a non-polar surface. This does you a tremendous amount of good. Number one, it deactivates the surface. This surface is chemically less active as a catalyst. Number two, it changes a polar surface into a non-polar surface, and that means that if you've got a low polarity stationary phase, that will now wet the surface. It will wick along the surface of a capillary. That will give you a much more uniform coating of that stationary phase on the surface. The last thing you want is a non-uniform film, because that means that some regions of the film are thicker than other regions of the film, and mass transfer in the thick regions goes with the square of the distance, and so if you have some place that's double the thickness of the average, mass transfer in there is 4 times slower. So the stationary phases, be they for packed beds or for capillaries, the stationary, the support is invariably pre-silanized. And I'm only offering you, as this is an example of how it might be done. The companies will not tell you how they do it. That is like one of the trade secrets. They don't patent it. They just don't disclose it. Okay, so sort of the end of the practical stuff for now. Well, reporting retention is also a practical issue. And it turns out that gas chromatography is much more complicated than liquid chromatography in terms of how we have to report retention. And I'll get into the reasons why that is so later. The retention volume is, of course, the sum of the dead volume of the column and the retention volume, the holdup due to the stationary phase. In gas chromatography, we invariably measure the amount of stationary phase not by volume but by weight. So this is the weight of the stationary phase, exclusive of the inert support. And beta is the equilibrium constant of the solute between the mobile phase, the gas phase, and the stationary phase. Now, frequently, instead of reporting the retention volume or the retention time, which we get by just dividing everything here by the flow rate, gives you the retention time, of course, is a thing called the adjusted retention volume. That is denoted VR prime, as defined as the retention volume less the dead volume, or the retention time less the dead time. These are both what we do in GC and LC. But GC's got a problem that LC doesn't have. The mobile phase in liquid chromatography is essentially non-compressible. But the gas, the mobile phase in GC is an ideal gas. And an ideal gas is a very compressible thing. You've got a pressure drop along the column. In a packed bed or an open tube, you measure your flow rate generally at the exit of your column. But the pressure at the exit of your column is lower than the pressure at the inlet of the column or at any point inside the column. You're at the lowest pressure in the system at the exit of the column. So the question is, what flow rate do you use? I mean, normally we measure retention time and we multiply it by flow rate to get the retention volume. But what flow rate do we use? In a liquid it's easy because it's incompressible. You can measure the flow rate at the exit of the column and use that. And the error involved is minuscule. It may be a few tenths of a %. But in GC the error is quite significant because of its compressibility. So the actual flow rate that you should be using is the average flow rate. So you have to average the flow rate from the inlet of the column to the exit of the column. It turns out that's fairly easy to do by application of the ideal gas equation, good old PV equals nRT. PV is a constant. Flow rate is just the derivative of the volume with respect to time. P times flow rate is a constant, so it's easy to calculate what the average flow rate is if you know the flow rate at the exit of the column, and you measure the inlet pressure and you measure the outlet pressure. And this factor J is called the James and Martin pressure correction factor. It's the ratio of the average flow rate to the outlet flow rate, and it calculates out for an ideal gas to be this factor. So you measure the PI and the PO, you calculate J, you measure the flow rate at the outlet, and then using J, you calculate the average flow rate. You take the measured retention time, you multiply it by the average flow rate, and that gives you the retention volume. The net retention volume is J, the correction factor, times the adjusted retention volume. And the corrected retention volume, VR naught, and these are all approved definitions, so everybody uses these definitions. The corrected retention volume is the measured retention volume, retention time times the outlet flow rate multiplied by J to correct the outlet flow rate to the average flow rate. So these are our different measures of retention volume. Let me make this perfectly clear. In LC, J is essentially 1. End of story. It might be 0.995 or something like that. Got one more. In the GC literature, they like to report something called the specific retention volume. That's V sub G. And that's the partition coefficient beta times 273.16, which of course is the conversion from centigrade to Kelvin, divided by the temperature of the column in Kelvin. This is an attempt to put everything, all measurements on the basis of a 0 degree centigrade standard reporting temperature. In other words, you don't report the retention volume or whatever at the temperature of the column. You report it this way, and so everybody's looking at the number at 0 degrees centigrade. That's about all the vocabulary you'll see in the literature as far as I've been able to find, but it's used a lot. And it's a real pain. It's very boring, but if you don't know it, you can't read the literature. Okay, so we're going to leave the practical world for a little bit and get into attempt to understand at a molecular level retention in gas chromatography. And we're going to start with the simplest model of gas chromatography. Actually, I should be calling it gas liquid chromatography, because we're assuming that the stationary phase is some kind of retentive liquid that's coated on an absolutely inert carrier particle, or inert wall of a capillary. So the process that we're talking about now is the transfer of an analyte molecule from the gas phase over to a solution, a liquid solution of the analyte in the stationary phase liquid. And beta, which is the distribution coefficient for this process, which is the equilibrium ratio of the concentration of the solute in the solution phase. And as I said a few minutes ago, usually concentrations and amounts of stationary phase are measured not per unit volume, but per unit weight of stationary phase. So Q is moles of solute per weight of stat phase. You could convert this to moles of solute per unit volume of stat phase if you knew the density of the stationary phase. And then the units would cancel and this would be dimensionless. This is the concentration of solute in moles per volume of gas. So this is moles per cc, and it corresponds to the solute concentration in the gas phase. Now, these have to be equilibrium concentrations. And if we know beta, then we can calculate the retention volume. The retention volume is VR is equal to Vm, the dead volume plus beta times the weight of stationary phase in the column. The question is, where does beta come from? Why is it big? Why is it small? What are the factors, the solute factors, that influence the value of beta? What are the stationary phase factors that influence the value of beta? So our model then, if you will, is sort of like this. Go back to the plate model. There's your stationary phase. There's your mobile phase. This is gas, this is liquid. And we have solute equilibrating between those two phases. So even though the stationary phase is a very, very, very thin film of liquid on some inert support, we're treating this exactly like stuff in a sealed test tube, letting it come to equilibrium between the two immiscible phases. Well, what things do we know about gases that are dissolved in liquids? Everybody is familiar with Henry's law. This is Henry's law. It says that the subscript 2 invariably refers to the solute. Says that the partial pressure of the solute is equal to a Henry's law constant, Kh, times the mole fraction of the solute in the liquid that is dissolved in. So this is essentially the liquid phase concentration. And the partial pressure of the analyte is essentially the gas phase concentration. So we just have to put them in the right units. So we've got to convert pressure to moles per unit volume. And we've got to convert mole fraction to moles per weight of stationary phase. Well, another way to write Henry's law is that P2 is equal to this number, gamma infinity sub 2, which is solute in the stationary phase at the temperature of the column P02 is the vapor pressure of the pure solute at the temperature of the column, and X2 is X2. Well, X2 will be equal to Q, the moles per weight of stationary phase, times the molecular weight, MW1 is the molecular weight of the stationary phase. And P2 we can relate to the concentration of the solute in the ideal gas phase And that's basically just the ideal gas equation. PV equals nRT. N over V is concentration. So concentration is the partial pressure divided by RT, the gas constant, times the temperature of the column. So we can stick this in for C. We can stick this in for Q. And it gives us this final result. So we now have the partition coefficient in terms of fundamental properties. So we need to know RT, that's not too hard. We need to know the molecular weight of the stationary phase. Well, that means you need to know what the stationary phase is, and so you calculate its molecular weight by adding up everything that's in it. You need to look up the vapor pressure of the pure solute at the temperature of the column. Obviously, the vapor pressure of the solute is a strong function of temperature. And then you need to find the activity coefficient of the solute at infinite dilution in the stationary phase liquid. Not so easy to look up. Okay, let's quit here and we'll get into the practical implications of this equation.